So basically, Jan, Plass, and I are representing quite a few people, and we basically are contributors to the Games for Learning Institute, which is based here in the New York area. It's got quite a few participants, but our mission is basically to put some solid science underneath Games for Learning. And I think I can, ooh, that was cool, wow. And we basically do lots and lots of different kinds of research: hardware, software, social games, math games. A lot of what we do is instrument the heck out of what we make, and then validate various theories empirically. And our goal is to make sure that when other people go forth and make games, there is some solid empirical science behind what they do. Now, the Games Learning Institute itself has lots of participants. There are a bunch of different labs. Every one of those labs has a faculty member. Some are at City University, at Columbia, at NYU Poly, at NYU. We have people who we work with in other places as well. And we form these complementary teams. What I'm going to do now is show you a little bit of some of the research side, and I'm going to do this. This is kind of a wacky talk because I actually decided I would use our research software to give the talk. So this is all just like experimental stuff, that presentation that I just wrote. See, whoa, you can do that. That's right. There you go. That's a presentation software. We can do more than that. So consider something like an interactive character. In fact, why don't I do this? Why don't I really take you behind the scenes? And oh my gosh, look what happened when they went to the thing. Everything got screwed up. Let's go here. Let's go do Find. I have to do this because when they plugged the thing in, everything on my desktop moved, but that's okay. We'll survive. Let's do, okay. So we build software that is based on all kinds of interactive stuff. Like, for example, here's one of our experiments. This is an interactive fish. The goal is to try to create non-player characters that have mood, personality, and that are interesting to people. So this is kind of a little experimental laboratory for playing around with this fish. Now you see there's these things to the left here. If I hit the H key, you see the fish gets happy, you know, and if I hit the A key, he opens his mouth, and if I look, you know, if I hit the 1 key, he looks there, or the 2 key, he looks there. So in fact, I could tell a little story with this, for example. I could start the timeline going, and now I can take a movie. I can say, you know, he looks at the ball, and maybe he's unhappy because nothing's happening with the ball. And he's like, looks at us, like, hey, nothing's happening with the ball. Maybe he looks at the other one. Meanwhile, of course, gets closer. Meanwhile, maybe this one, you know, starts like behind him, sees, you know, something's happening. So he goes there, and he's like, whoa, this is so cool. And he gets like really happy, you know, and then he's like looking at us. Hey, this is really great. I'm just really happy now. And what about the other one? And he's like, oh, no. But then, of course, looks back at this one. Maybe we grow this one, you know. So now he goes back here, and he's like, yeah, everything's really great, and we make it bounce, and he's like living in this happy world. This is basically, I'm doing wish fulfillment, because it's like, you know, like I want to live in that world, you know, and then he's like really happy and stuff like that. But the point is that what we've done is pushed up things to build a level of support so that as I'm making these decisions, I'm doing high-level puppeteering, and I'm designing a whole bunch of material that will go into some interesting games that we can apply them and ask questions like, well, if the fish is happy when I do something, or if this gets frustrated when I do, or if the fish is encouraging, et cetera, et cetera. And in some of our recent Games for Learning work, we've taken this, and by the way, this now ends up being, you can edit this, you can go change the movie. This exists online, by the way. You can actually make collaborative work with your friends, where you can be one of you can be puppeteering while the other is changing the timeline over the web. But then we say, okay, let's apply this to to actual learning games. Like one of the projects we did recently is try to help make a prototype about how do you use an interactive character in a game to teach kids literacy. So for example, if you have these little puzzles like, you know, which one of these on the top matches which one of these, and these are all basically research instruments. So you can say, suppose instead you had these things on the top and these things on the bottom and you try different things. Or suppose you wanted to make it a letter matching game, like which one starts with a letter, et cetera, or you want to make it 1 instead of 2. So these things have all these different flavors, but one thing they have in common is that behind the scenes, you can be puppeteering the fish. So, you know, you can have him drift right or drift left. You can have him look down there and like, you know, so he's really unhappy, you know, and he's like, oh, I'm really unhappy and I'm looking at this and I'm not getting the right answer anywhere, you know, and it's very compelling, actually. I don't know, I think it is. And I love, the weird thing is when he looks at us, in fact, specifically, we wanted to build in the capability that could actually run off and hide. So it's like you're supposed to give him you're supposed to pick something and he's not supposed to know. So we have the thing where he like runs off and hides in the back. And so we're going to leave him happy because otherwise people tend to get depressed afterward, according to Jane McGonigal. And but now you notice what's going on here is that there is no actual AI. We started building versions with AI and realized that it was actually quite difficult for our grad students to author the AI that we built, which is basically having a machine press these buttons. So instead of me hitting the keys, you have the computer hit these keys. So we took a big giant step backward and said, maybe it's time to re-engineer. So we went back and learned from a project that Jan Plass and myself had been done a number of years earlier with Mary Flanagan when we worked together before the Games Learning Institute on something called the Rapunzel Project, which was a project to help give middle school girls a more positive experience about learning to program. And so this was one of the experiments for that. And here, what you're seeing is, on the right, you're seeing a happy flower. I can tell it's happy because I speak flower. And then on the left is code. Now this code was there's an interactive version of Java written by a brilliant guy named Pat Niemeyer, which is freely available. So I rebuilt, our team rebuilt a geometric modeler to make use of it. So for example, I can do anything here. I can say, oops. You know, I can change the program, or I can make him wiggle like faster, for example. Whoa. Or I can have him twist. And I'm actually changing code here to do this. And the important point is that there's a direct correlation between what somebody, oh, you want more petals? We'll just put in more petals, you know, 20 petals. I mean, everything happens immediately. And this has this quality that some of you might recognize from Mitch Resnick's Scratch program, that there's an instant update. So you're constantly getting, like, oh, if I want, I can even do something like plus, notice while I'm not doing something valid, it waits for me. 1.5 times wiggle, I don't know, 0.3 times time. I'm just making this up. There you go. Or 1.3 times time. Whoa, whoa. Anyway, you get the idea. So the thing is that you can change all these different things. We thought, well, why don't we take this idea and not only use this to teach programming, but why don't we bring this into our own practice so that we start using this as our own prototyping tools. So we retooled everything, and you're seeing now just at the beginning, because we just started to do this. I'm going to start to show you some examples of what happened since we started giving ourselves a tool that will allow us to just throw stuff together interactively with instant update. And I'll show you a little bit how that works in the time that I have. So, so here, for example, is, I guess I can get rid of that. So here, for example, is the flower in our current system. Let's make it big. Ooh. Okay, there we go. So this is the flower in our current system, and it's the screen size here is a little different from what I'm going to do is I'm going to run it small because you can't see the big screen. Unfortunately, because of the change in resolution when we went to this display. So you'll have to deal with it small. And make it even a nice blue background. And now I'm going to hit keys on the keyboard, and things come to life. So, you know, it sways back and forth, or it turns left and right. Or I can now start, because now I've really started going to town with this thing, You can start doing things like making it thicker, or making it thinner, or making it really tall or really short. But this time, we're exposing everything. So there is actual interactive code running underneath, which I will show you. How many people start to panic when I say there's code? Just curious. Okay, right. So this is the actual code. This is actually the geometric model of the flower. And the key idea here is that whatever you do, it immediately gets interpreted. So there's like that little yellow stem. I can change that yellow stem, you know, that yellow thing in the middle there. I can change that to, you know, to white, and it immediately changed. Or I can change that to red, for example. Or I can go and I can make a very unusual, can everyone see what I'm typing? You see what I'm typing on the right there? Or I can change that ball to a box. And now we have a very unusual flower. So you get the idea. Well, am I out of time now? Or are you just coming up? Okay, all right, a couple minutes. All right, so, but now it turned out this was so useful that it turned out to be useful for solving all kinds of problems. So for example, here, I was actually interested in this design problem of, you know how there are text fonts? I was interested in the problem of chess fonts. So how can you change one characteristics of one piece and change the entire, how do you like analyze and then resynthesize a chess set? And so here, for example, is a pawn that I built using this modeling system. But the nice thing about using this modeling system is you can start looking at the different parts of the pawn, and you can start asking these questions like, oh, maybe a pawn consists of 5 parts. There's the base, the skirt, the stem, the collar, and the head. And then you could start, using an interactive model where everything changes, I can just start going between all of these different fonts. And basically, when we finish this project, then as you change the pawn, the bishop, the queen, and everybody changes. Anyone have that experience of you're playing chess, and there's like one pawn missing, and someone takes a pawn from another chess set? And it's like you can't think about the game, because it's like, so this way we can do it right. And also, let's see, and the nice thing is this makes it very, very easy to throw together lessons. So for example, this is a binary counter, and all the code for implementing that, soup to nuts, was down here. And the nice thing about having interactive Java is we can just redefine it. We can change it. We can extend the language. So we realized for AI, not just modeling and animation, for AI, you want scheduling ideas. You want, say, do something when something happens. So we introduce a when statement, which doesn't actually exist in Java. That just says, whenever something becomes true, then do something, which is how this flipping is happening. And here's a more dramatic example of that. What? No, because it has memory. So it only triggers once, like you would have like in a neural net. It says, okay, false, 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 true, 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 true. When you get the transition from the false to true, without you having to set up a state variable, it just does it for you.
What is the website where you have all of these?
I don't have this. I have lots of my stuff on a website. I don't have these guys on a website yet, but we're going to hopefully be releasing this in the next few months. Actually, let me jump to some of the, if it works, because I think in the interest of time, I should jump to some of the really cool stuff, because I wanted to show you, inspired by the previous talk, we decided we're also going to try to do stuff with Microsoft Connect. And so we've started trying to figure out how to integrate the Microsoft Connect with the stuff we're doing. So this may not work, so forgive me if it doesn't. Kind of a Toys R Us moment. Here you go. It's not a commercial endorsement. All right, there you go. Okay, so we'll see. So just so you know what's going on, some really brilliant grad students have written their own wrappers. Murphy Stein and Jonathan Thompson in our computer science department have written their own wrappers around, it's never going to happen now. Oh my God. Well, let's do it this way. Hold on, sorry. Just that everything that was laid out on my desktop is gone. So let's see if I can do this. Desktop. If this doesn't work, then I'm not going to be able to show this to you. But let's try it. So what they did is they wrote a wrapper around the software that already existed for tracking a Microsoft Kinect. So you're seeing now what the Kinect sees, and if I do things right, it's, you know, it's tracking my. So the thing that they've added that doesn't exist in the standard software is it can track individual fingers and all kinds of subtle, like for real close-up work, all kinds of subtle knowledge about your hand shape, et cetera, which it's not what the Kinect was originally designed for, but we find it's really important for the kind of stuff we're doing. So imagine this is running behind the scenes. This is a background process. It's just running behind the scenes. And then as I launch something, that's going to be running behind the scenes. So let's see if we try to run this and see if it works. You get the idea of now one of the problems here is that if we do this, very important research instrument, ping pong ball. The reason we need the ping pong ball is that the lighting here is very specific lighting. And if a teacher wants to give an augmented reality presentation, they kind of want the objects to kind of look like they exist in the scene. So if we enable the Kinect, so now you're seeing the Kinect, but the lighting is all wrong. So if I do this now, I'm going to create, you see there's that little red thing. I'm going to do this. This is really nerdy, but trust me. And then I'm going to capture that ping pong ball. There you go. So now the lighting is correct for this like weird lighting setup that we have here. So that now as I basically take these objects and assuming that I didn't just totally, wait, is the tracking still working? Is it? Oh, look at that. See? This is one of the issues with the Kinect is you kind of have to carry up. There you go. So now it knows about my left hand and it's basically running software to blend these things together, and I can be moving objects in space, in my own space. Now, the thing I want you to think about, this is very early stuff, is I want the educators here to be asking questions. What kinds of experiments would I be able to do if I'm able to take computer graphics and put them right in the scene with me, and there's an object that's just floating around in the scene in front of me, but it can have whatever augmented powers I want, and then finally we can do things. We can do things like. And then eventually, and then I have to wrap up so that Jan can get up and talk. I'd like to do things like be able to basically bring objects in, which I'd like to do eventually by having tracking. I'm showing you this idea about stuff we might eventually want to do, and you know, we'll let people interactively design things. And then as they're interactively designing these objects, they can sort of assemble them, put them together, and you know, make something interesting out of them, and then just assemble 3D lessons right in space, and you know, teach something with them. So this is where we're going. We're going to. Our goal is to go to a place where we can write a series of tools and tutorials so that educators can start having this kind of speed and of both making and using a community of education content for themselves. And I will then hand this over to Jan.
Thank you, Ken. I typically don't like to go after Ken's presentations. For a number of reasons. The most important one is that I don't have cool things flying around, so I have to apologize for that in advance. What we do have, though, is data on some of the things that we have shown, and data on how particular designs result in particular types of learning, and that's what I would like to talk about briefly. So the whole idea is that in designing games for learning, any game that you design, you need to make certain design decisions, and the more you can base those on actual empirical research to understand what impact those decisions will have on learning, the more likely the game actually will produce the kind of learning you're looking for. So when we do that, we look at games as a question of not just genre, but also what the function is that the game has for learning. And that is an often overlooked kind of point. Are we trying to prepare future learning, which is what Jim talked about in the morning in part, or are we trying to actually teach a new subject or a new skill, which is almost no game is doing that these days. Or are we practicing existing knowledge or skills, which most games are currently doing, or is it about development of learning and innovation skills? Some people like to call it 21st century skills. I believe they exist before and they need to exist after, so learning and innovation skills. Any of those functions as primary functions would result in very different very different, now I feel untracked, I don't know if I can handle that, would result in very different genres that I would use for the game, and very different designs that I have for the game, and obviously very different outcomes that I expect of the game. And unless we're communicating that clearly, I can't really even assess whether a game works or not. So we have built a variety of games that serve some of those functions, some of them just as prototypes, most of them just as research prototypes. Ken mentioned Rapunzel. We built some augmented reality games, some skills games on math, factoring and super transformations, on geometry, etc. Mary Flanagan earlier showed the Flagella game here. And for all of those games, we go through a series of research phases that all start with usability testing and then move on to play testing, obviously. So we just play tested this game and gave feedback to the team. But one of our more exciting kind of activities that we're currently focusing on is an after-school program that we call Create to Learn, where we go into after-school programs of middle schools, primarily with young women, with girls in these programs. And we have a year-long program where they learn about game design, and they design their own math games and do research with those math games. So we teach them about research as part of the design process. And here you see their prototyping, on paper prototyping and trying this game out. And actually getting feedback from 8th graders, getting feedback from 6th graders, and so on. So we're using the whole game design process as a way of getting into the whole idea of learning math, because if you want to build a math game, you have to understand the math behind it. And then all of a sudden, you have a reason to actually understand that. And you collect data, and you can find out how that helps you improve your designs as well. So the result then is built by First Playable Productions. Here the goal was not computational skills, but to be actually able to think about game design and mechanics and teaching math with that. And that's a game that you can see now in the exhibit across the hall being presented. And some of our students are actually there and are very excited about it. So the kind of research that we're doing has a lot of different areas of interest. We think about some models that underlie game design. We think about social factors, cognitive factors, affective factors. And I briefly want to go through those, not to go into great detail with them, but just give you a sense of what the questions are they were asking, the answers that we're looking for, or better finding. And the important thing here to mention is that we use any kind of research method that is appropriate for the research question, rather than saying we are this kind of a research group that does this line of work only. So it starts from critical analysis and playtesting, naturalistic inquiry, all the way to design experiments, evaluation, digital video ethnography, correlational research, and then every now and then some effectiveness and efficacy research. One of the things that we're thinking about in terms of models is how we can think what interactivity means, and how we can think about what engagement means. And those people who can't hear well in the back, there's so many seats here in the front. Also, the microphone apparently doesn't go up anymore, so I'm going to do this. Yes. Did you hear about the study that the less legible the font is in a paper, the more cognitive effort you actually invest in reading it, and the more you learn? I tried that with the acoustic signal, and apparently that didn't work so well, so sorry about that. So we distinguish between different kind of interactivities that result in different kind of engagement. When we look at behavioral interactivity versus cognitive activity versus emotional activity, all of which we can have in a game, we need to understand which one actually contributes to learning, and that just being busy behaviorally doing something, which could be grinding, might not necessarily respond with learning outcomes. So we build models like this. We have a game design model that's based on Tracy Fullerton's model that I use with my students to essentially turn her model into one that is appropriate for games for learning. And we think very deeply about the whole idea of game mechanics, and I had a long conversation with people who are actually designing games and are asking the question, well, who should design it, the learning designer or the game designer? And the way we think about it is we actually want the learning designer to think about learning mechanics. That means the activities in the game that relate to learning. And then we give it to game designers, and they know how to turn that into a successful game. So for instance, the learning mechanic might be that I want to engage someone in some civic discourse. And the game mechanic would be that I either use IM, or I use bubbles, or I use any other way of avatars or so to do that. That's up to the game designer. Similarly, we're thinking about assessment mechanics as something that test designers need to come up with, people who know how to actually do assessment. But we know that when you let them do the entire test, what you get in the end is a multiple choice kind of test. So what you really want is then a game designer to turn that into a game mechanic so that I actually get the right data out of my log files. That's a talk that I gave at GDC, so I don't want to go into much detail with that, but it really helps us understand the whole design process and who does what. And the resulting thing is a game that we built later where we look at angles and quadrilaterals as a game, and here in a triangle, in order to solve that, I could either be asked to have as an answer to say this particular angle is 30 degrees or so, which means I need to know which rule to apply and then do the arithmetic on solving it, or I can just say which particular rule I can apply, and you see the icons for those rules, and I may have a fling mechanic just as in Angry Birds and fling that to the triangle, or I may have put some jetpack on it or do other things, and that would be up to the game designer to decide. So the separation of what it needs to do versus what it actually looks like and what the mechanic is that's involved in it on a play level. So in our various labs, we do research then on those mechanics that involve embodiment and movement. We have augmented reality games that are like Brooklyn Blooms, that are embodiment games, research-related things. This is all Catherine Isbister's work. We've built those studies, those games with the game mechanics, and we compared different game mechanics. So we actually wanted to know if I give someone a rule as an answer versus a number as an answer, a response to a problem to solve, what different results that has that in the game play and in the learning outcomes. And so what we find is that it's actually more interesting to use the numbers as an outcome, an arithmetic kind of response, but they solve more problems when they have a rule-based response. In other words, they drag the right rule onto, or click the right rule to solve a problem. And we found, interestingly, that there's diminishing returns when I use the arithmetic version of the game. In other words, I learn more and continue to learn when I apply the rules. In other words, that rule knowledge continues to be enhanced. We did other research where we have a question regarding mode of play, and I'm going to skip through this a little bit. So we compared solo play, collaborative play, and competitive play, and we found that it's not always the question of what is more interesting and what is more exciting, but there might be different outcomes when we look at the actual learning outcome in various tests that we use for this. But the game that I wanted to talk about a little bit more is about literacy development, and that's some very recent research that we're excited about, using the Kinect to actually have very young kids, kindergartners and first graders, read. And so we compared here the question, or asked the question whether a game that can teach very young kids to read would actually compare well to a caretaker reading to the child, and whether activities within that game would either distract or help the whole learning process. And so we had those kindergartners come to our labs and had those caretaker groups, a game with activities and without activities, and then had various tests in terms of vocabulary in the outcome. And here you see a schematic of the presentation screen in the front and where the kids were standing, what kind of activities they were doing. And so they were in the game as their own characters picked up by the Kinect. And what we found in the end is that the game that actually used activities with the reading process, activities that were concerned with the words covered by the story, had a number of benefits compared to the caretaker reading, and were far better than when a game without the activities was presented. So just reading it off the screen or getting it read to you from the screen did not do as well as having the activities with word, like scurrying around or doing other things, and having a caretaker read to it. So a very encouraging result to show that it might be possible to actually have some literacy skills developed with these movement-based games. We also do a lot of usability work in these games where we ask for questions, especially with the Kinect, the kind of gestures we're using, the kind of assistance that's required, how much do kids ask for assistance, how much assistance do they need to get, how natural do the gestures come to them for the in-game activities, and there's a lot of refinement that comes out of that that then is being handed back to the game developers to refine their games. We did other work in science simulations, and we built several of those simulations. This one is for diffusion. And here we ask questions regarding the integration of information. You see in this particular simulation, there's the simulation area on the left, and then there's a chart on the right, and you see a graph develop as you measure your data points. And many people will tell you that that's actually generating a lot of cognitive load because learners need to integrate those two representations. And that's exactly the questions we were asking, and we used an eye tracker for that. So we do a number of eye tracking studies in our lab. And we actually tracked where people were looking while they were using this simulation. And what we found was very surprising and completely in opposition to what people would have believed, who said it was distracting to have the graph area. When they were fixation transitions from the simulation to the graph area, it actually enhanced comprehension and transfer of the material itself, and the more frequent it was, the more that was related to better transfer and better comprehension, and specific areas were actually related to specific learning outcomes. So integrating those two representations was very useful for the learners, and having frequent eye movements back and forth. And so that really helps us when we design games to understand what needs to be placed where and what kind of representations can we have on the screen so that we actually support learning rather than hinder learning. So there's a whole team involved in that research process that I wanted to acknowledge, and I didn't even mention the individual labs because Ken had already introduced them. But I wanted to finish with one more thought, which is we're starting several games programs here at NYU. There's an MFA in game design. There's a Masters of Science in Games for Learning that is starting soon. And then there's also a Bachelor in Game Engineering that's in the planning process, and anybody interested in that could contact me or anybody else here at NYU, and we're happy to tell you more about it. And I think with all of that, we have just about exhausted the time for our talk, and I wanted to thank you. And we'll move on to the next one in just a moment.